Okay, since now in calculating the surface integral for vector field, we don't use the small n anymore, which means that we don't use the f dot small n ds, but we use the we use the from f dot n ds over the surface sigma. Now we want to use the f dot capital N dA over the region R. So meaning that we don't need to have this one. You don't need to compute the ds for vector field. And similarly, you can what I want to say here, you can ignore this calculation or you can skip this page. I'm not saying this is wrong, this is also correct, but since we have a more simpler way, just using the normal vector n, capital N. So you can skip all these steps. Okay, so now we look at the example 14. So you have to calculate the surface integral f dot n ds over the surface sigma, where your surface is a part of the or portion of the z equal to 1 minus x square minus y square. So what is the shape of this surface? Lies above the xy plane. So it is a bowl, right? But your bowl is just lying above the xy plane. So when you sketch the bowl, lying on xy plane, and you have this bowl. So this is one. So on the xy plane where z equal to 0, so you will have 1, 0. So we set z equal to 0. Then 1 minus x square minus y square, and you will get x square plus y square equal to 1. So this one, 1. Okay. Why I have to cut the bowl by this plane? Because it stated that the surface, which is a bowl, lies above the xy plane. So meaning that you have this particular shape. This is open surface. Okay. So suppose that your surface is oriented outward. Okay, that is the condition for you to compute the surface integral, where your normal vector always point outward to the surface. So you have to evaluate this where, okay, in your question, the function of the sigma and the vector function must be given. Otherwise, you can claim that the question is incomplete. Okay, so now the problem is we want to get capital N, normal vector. Okay, so in order to get the normal vector, here you have to look at your equation of your surface function given. So in this case, it is already stated that your surface function sigma is the function of xy. So we can take note that your region must be on xy plane, right? And then the component in gradient phi, you must focus on the sign of the key component, because in this case you have z. Okay, so now to get the phi, so you have to make this function, this equation equal to 0. So now your phi is, in terms of x, y, z, is z minus the function of xy. It is equal to 0. So you have to bring everything to the left or to the right. Then you will get z minus 1 plus x square plus y square equal to 0. Where you bring, I bring everything on the right to the left. So I will get this. Okay, so that is our phi, and then we compute for the gradient phi, where you have to phi x, you have phi y, then you have phi z. Okay, so differentiate phi with respect to x. So differentiate all these scalar function with respect to x, 0, 0 to x. So you have 2x, and respect to y, so 0 to y plus 2y, and phi z, this is only the z, so we will get 1. So that is your grade phi. And then how about your n? Now ask yourself, your n is the gradient phi itself, or you have to make it negative. Okay, so now according to the function that you choose here, you have z is a function of x and y. You have z, so meaning that in order to determine this one, you have to look at the z component, whether it is positive or negative. Then you have to refer to your sketching, okay, of your surface. So since this is your surface, which is a bowl, and the normal vector always point outward to the bowl, point to this way. Okay, if you have another point, so your n, this is your n, and this is your n. So you can evaluate your normal vector for for any point here. Okay, and you can see that because we want the n always point outward, so we only focus on the key component. So according to the arrow that we have here for any for the value, okay, not the value but the vector, the normal vector at this specific point, so the key component always point to positive z or positive k. So meaning that we must have always positive k, or k positive. K must be positive. So that is the thing that we wanted. Okay, we want it. So now look at your calculation of your gradient phi. So it is already positive. So meaning that you can accept the gradient phi here will be your n. So your n now is given by gradient phi, where it is 2x, 2y, 1. So that is your n. Okay, then from your surface integral, now we can rewrite this f dot n dA over the region R, and your region must be on xy plane. So now the next step, you have to find the dot product between the f and the n. Okay, so what is the f given? So the f given, just copy from the question. So the f is x, y, and z. So when you apply the dot product, so you have to multiply the component f with the component n. So you have 2x squared plus 2y squared plus z dA for the region on xy plane. Okay, so now once you compute the dot product between f and the capital N, you have this scalar form. So now the question is the similar as line surface integral for scalar field. Can we directly integrate this? Because for the multiple integral concept, if you have double integral, so the total variable possible, the total variable allowed in the to be your integrand here must be not more than 2 if it is double integral. So as you can see here, you have 3. So meaning what? We have to convert. We have to change. Which one need to be changed? The x, the y, or the z? Okay, now look at your region here, or your function. That's why I always put this one, just to note myself that the possible variable are allowed here only x and y. So meaning that you have to replace z. So what is the equation that can be used to replace the z? Should be your surface function where z equal to 1 minus x squared minus y squared. So you have to use this to replace. So now your equation become 2x squared plus 2y squared plus z. So your z is 1 minus x squared minus y squared d. Okay, now this makes sense, right? Because you have double integral and the total variable that you have here only not more than 2, x and y. Okay, then we simplify. We have x squared plus y squared plus 1 d over the region xy. So now we managed to convert from surface integral for vector field. This one, this is from the original question, and then we convert into f dot n dA, and then we obtain the n. So we finally obtain this, but you have to replace the z. The z is not allowed because only x and y, so you replace by using the sigma function given. And after that we managed to reduce the surface integral into double integral, into the regular double integral that you have learned before. Okay, so now we need the order of integration. In order to determine that, you have to look at your solid. You have to find where is your region. So your region must be on xy plane. So what is the dominant shape which is lying on xy plane? You can see the circle, right? The circle here is the dominant shape, isn't it? So now we sketch the region. Remember I told you before, the sketching, especially for the region, is very important. Okay, so on y-axis plane, we have a circle, radius 1, where you can get from here. Okay, because it is lying on the xy plane where z equal to 0. So since our region here is a circular region, I want to apply the polar. I want to solve this using polar coordinate system, because for me this one is more easier. So when you convert into polar, then you have r squared plus 1 r d theta, and look at your region. You have a complete circle, so 0 to 2 pi, and your r is 0 to 1. Okay, so I'm sure that you have no problem to integrate this. You can use substitution or you can expand. So r cubed plus r dr d theta. So I am expanding this. First integrate with respect to r. 1 over 4 r4 plus r squared over 2. So r is 0 to 1 d theta. So we simplify that. You got the 1 over 4 plus 1 over 2 d theta 0 to pi, and 3 over 4 to pi. So 3 over 2 pi. So this is the answer for this particular example.